Okay, welcome back to Chapter 5. Today we're going to talk about the gas laws. So in your outline, you should have read about 3 gas laws: Boyle's law, Charles' law, Avogadro's law. And what these 3 laws do is they talk about, for gases, what's the relationship between a couple variables. So for example, Boyle's law is talking about volume and pressure and what the relationship between these two things are. So, for example, you can envision a balloon, and if you have a balloon at, let's say, at the surface of the ocean, right? So here's the surface of the ocean, here's our balloon. So the balloon is under atmospheric pressure here. Let's say atmospheric pressure is 1 atmosphere. So under an initial pressure of 1 atmosphere, the volume of the balloon, let's say, is 1 liter. Okay, now if the balloon is taken down into the ocean under the water, the farther down in the ocean the balloon goes, the more and more and more pressure it's going to feel. It's kind of like if you're swimming, right? And if you're swimming, if you dive just under the surface of the water and come back up, you might feel a little pressure on your ears from the water. But if you dive all the way down to the bottom of the pool, your ears are going to feel a lot of pressure, because you have all of those molecules of water stacked up above you, being pulled down by gravity. A foot of water stacked up on top of your eardrums isn't going to feel like a whole lot, but 18 feet of water molecules stacked up above your eardrums is going to feel really heavy. You're going to feel that pressure, that force in that specific area. So as we bring this balloon down in the water, it's going to experience more and more and more pressure. And so what's going to happen is that pressure is going to squeeze the gas molecules together, and the balloon is going to get smaller. So let's say the pressure here is 2 atmospheres. So that's our second pressure. Our new volume is going to be smaller than the initial volume. Let's say it's 0.5 liters. Okay. So this is what these gas laws do. They compare 2 variables. In the case of Boyle's law, it's going to be comparing pressure and volume. And they talk about, okay, in the first scenario, in our initial state, what are these 2 variables? And in our second state, when one of these variables changes, the other variable is going to change in response. Okay, so it's basically showing you the relationship between 2 very specific variables when it comes to gases. This whole chapter is talking about gases. So you can sum these up and say, okay, well, Boyle's law is an indirect relationship. As volume goes up, pressure goes down. As pressure goes up, volume goes down. Charles' law is going to be a direct relationship. If temperature goes up, volume goes up. If temperature goes down, volume goes down. Again, this one's a really good one to envision in a balloon also. You can envision a balloon, if taking a balloon from room temperature and then putting it in the freezer. So temperature goes down. What's going to happen to the balloon? The balloon's going to shrink, right? Volume's going to go down. Or you can think of it in terms of like a hot air balloon. If you take the air in a hot air balloon and you blast it with fire, right? Those air molecules are going to start moving faster because they have more kinetic energy. That's what temperature is a measurement of. These molecules are moving faster, and so therefore they're going to move apart, and the volume is going to increase. So that's a direct relationship. And then Avogadro's law is also a direct relationship. If you increase the number of moles, volume's going to increase. If you decrease the number of moles, volume's going to decrease. You can think about this in terms of like filling a balloon with marbles, right? If you have 100 marbles in a balloon, your balloon's going to be a specific size. If you increase the number of marbles, say to like 1,000, your volume's going to increase. So it's, again, a direct relationship. Now, the catch with these things are you have to remember these relationships. You have to have them memorized inside your head, or you have to be able to derive them from something. And that's where I want to go today. I want to show you how you can derive these relationships instead of memorizing them. And so all of these relationships come together in one big law. You look at Boyle's law, volume and pressure. You look at Charles' law, that adds a temperature factor. You add Avogadro's law, it adds a mole factor. So all of these different variables can be related in one law. It's called the ideal gas law, and it is PV equals nRT. It's basically, if you notice, all of these above are volume related to pressure, volume related to temperature, volume related to moles, right? Well, the ideal gas law is volume related to what? And here's where your algebra skills are going to get really good. We need to be able to manipulate a formula. So remember, you can manipulate any formula. You just, whatever you do to one side, you have to also do to the other. So these are going to be the math laws that guide us this chapter. If you multiply a side by something, you have to multiply both sides by it. If you divide by something, you have to divide both sides by it, right? So hang on to those kind of algebra rules, and we're going to move forward and manipulate a whole bunch of equations. So for example, let's manipulate the ideal gas law. So it is also volume related to something else. So basically what we need to do is get rid of the P. Now would be a good time to pause this video, try it, and then start playing the video again. So I'm going to divide both sides by P. I want to get rid of it. And if it's being multiplied right here and I divide by it, P over P is going to be equal to 1. It reduces out of the equation and leaves me with V on this side. And then notice that the other side is going to be nRT over P. So notice all of these laws, Boyle's law, Charles' law, Avogadro's law, they're all represented inside the ideal gas law. We have volume indirectly related to pressure, right? Volume indirectly related to pressure. As pressure goes up, our denominator goes up, our answer, volume, is going to go down. That's an indirect relationship. We also have Charles' law here, volume and temperature. This should be a direct relationship. So we have volume on this side and temperature on this side. Since temperature is in the numerator, it's also a direct relationship. As temperature goes up, what happens to our answer? Since temperature is in the numerator, our answer is going to go up. Okay, and then we also have Avogadro's law. We have volume proportional to moles. So this should be a direct relationship. And again, we have volume on this side, and then moles is in our numerator. So when moles goes up, our numerator gets bigger. What happens to our answer of volume? It also gets bigger. So all of these are encompassed in one ideal law. So my suggestion to you, as your tried and true chemistry teacher, is don't memorize Boyle's law, Charles' law, Avogadro's law. Memorize the ideal gas law and be able to derive these out of the ideal gas law. Now, there's a couple notes I want to make here. Note number 1 is R. Notice R. R is the constant in this equation. It's the number that goes in there that just makes this equation work. R is the ideal gas law, and it's going to be on your sheet. It's going to be on your reference sheet. It is right here also on this slide, 0.08206 liter atmospheres per Kelvin mole. So notice if you get R by itself, okay, let's do that. So we start with PV equals nRT. We want R by itself. We have to divide both sides by T to get rid of T. we have to divide both sides by N to reduce out N. So we're going to get PV over NT. And notice if I plug in units for these things, so pressure is going to be in atmospheres, volume is in liters, N is in moles, T is in Kelvin, I end up with the units of R, liter atmospheres per Kelvin mole. So again, where did the units come from? What do the units mean? The units are just there to make the equation work. And what does 0.08206 mean? It doesn't mean anything. It is a number that makes the equation work. We can, because we have R in there, we can use an equal sign. We don't need to use a proportional sign like we have over here with Boyle's law, Charles' law, and Avogadro's law. The other note, another note I want to make is notice that there's two R's. There's two gas law constants. They are the same number. Well, they're kind of. It's the same ratio. It's just in different units. So basically what we've taken is we've taken liter atmospheres and converted out of liter atmospheres and into a joule. And when we convert from one unit to the next unit, our ratio is still equivalent. We're just communicating that ratio in different units. So you have to be really careful to make sure you use the correct R. You want to use the R that gets your units to be what you want them to be. If you're in the ideal gas law, you need the units that are going to reduce out with the other units you're using. You don't want to use joules because you don't have joules in the ideal gas law. You want to use liters and atmospheres. So make sure you pick the correct gas law constant. Last note before we move on is I want to circle back around to this concept of molar volume. In chemistry last year, we talked about how when we are converting between, I'm just going to quickly write our mole hole, right? So we have gas, I need a pen. Grams of A, we can convert to moles of A. We can convert to particles of A. We can convert to volume of A. We can also convert from moles of A to moles of B, grams of B, particles of B, and liter volume of B. Okay, so the conversion I want to focus on is this, moles of A to volume of A. Okay, so we've talked about this conversion factor in terms of solutions. If you're dealing with a solution, you have to use molarity, right? Molarity is the ratio that gives you moles per liter for a solution. In chemistry, we talked about molar volume being 22.4 liters per 1 mole of a gas. And we really hammered that you can only use this for a gas. 22.4 liters of a gas is equal to 1 mole of a gas. Well, there's one more catch that you really need to be careful of. This molar volume is only true at STP. So you can, if you are at STP, standard temperature and pressure, so 0 degrees Celsius, 1 atmosphere of pressure, if those are your temperature and pressure conditions, then your volume is going to be 22.4 liters. Your moles is going to be 1 mole. If you're not at STP, if you're not at 0 degrees Celsius and 1 atmosphere of pressure, you cannot use molar volume. You cannot use this relationship between volume and moles because remember, we just saw up here with these little laws, right? If you change the pressure, you're going to change the volume. If you take 1 mole of any gas and you put it under the sea, the volume is going to change because your pressure has changed. You're no longer at STP. Your volume's no longer 22.4 moles. Same thing with temperature. If you take 1 mole inside a balloon and put it in a freezer, you have just changed the temperature. The temperature is no longer 0 degrees Celsius, I'm assuming. Your temperature is now something different. So therefore, your volume is not going to be 22.4 liters either. Your volume is going to change. So you got to be really careful of that in this chapter, especially. 22.4 liters per mole, the molar volume of a gas, is only true at STP. If you're not at STP, you must use the ideal gas law to calculate a new volume. Now, the nice thing about the ideal gas law is it's very cut and dry. There's not too many ways we can manipulate this formula. A lot of these problems are going to be plug and chug. You plug in 4 values, you chug out 1. You are the hardest math we're going to ask you to do besides dimensional analysis really is going to be manipulating this formula. Can you isolate V? Can you isolate P? Can you isolate N? Can you isolate T? And then plugging and chugging. So that's one nice thing about the ideal gas law. Okay, one more thing on this slide. You're going to run into questions that give you a set of conditions that is initially true, and then they change those set of conditions. So again, you don't have to memorize new formulas for all of these conditions. That would be a lot of new formulas, right? You just have to be able to manipulate the ideal gas law. Are you noticing a theme here? There is a theme to this chapter, and it revolves around manipulating the ideal gas law. So I want to kind of walk you through one of those scenarios. All right, so for example, let's talk about, let's do Avogadro's law, just for fun. Okay, so if you have a scenario where you have a set of a volume. Okay, let's go. Our initial volume is going to be, 1 liter. And then if we have 1 liter of gas, then we're going to have an amount of moles of, let's say, 2 moles. We'll keep it simple. Okay, and then into this system, we're going to pump a bunch of gas. So let's say, this is, I didn't mean to put N2 there. So our initial volume, or V1, is 1 liter. Our initial amount of moles, or N1, is 2 moles. So now a whole bunch of moles gets pumped into the system. Let's say our moles increase to 5 moles. What is our new volume going to be? Now, in order to solve this, you could just memorize Avogadro's law, and then you could plug in these numbers and chug out an answer. But instead of memorizing Avogadro's law, I want you to be able to work through this system with the ideal gas law. So let me show you how to do that. We're going to start with PV equals nRT. Okay, so in our initial system right here, we have a set volume, we have a set amount of moles. Now the question is, what's our P and our T? What is our pressure and our temperature? Okay, so before we answer that question, I'm going to manipulate the ideal gas law. So I'm going to isolate volume and moles on one side, and I'm going to get everything else on the other side. So I want to get rid of pressure. I'm going to divide both sides by pressure. That eliminates it out of this side. I want to switch moles to the other side. So I'm going to divide both sides by N. And I'm going to end up with V over N equals RT over P. Okay, so I have just manipulated my formula so that volume and moles are on one side. So volume and moles are on this side. And they are equal to R, whatever the temperature is, divided by whatever the pressure is. Okay, so the question is, what is pressure and temperature initially? And what is pressure and temperature when this second scenario comes to pass? And the answer is, we don't know, but it doesn't matter because it doesn't change. All our scenario told us was that the amount of moles change and the volume changes as a result. And so what we need to assume is that pressure is going to stay the same and temperature is going to stay the same. Sometimes the problems are really nice and they say pressure and temperature are held constant. That would mean pressure and temperature initially is the same as pressure and temperature in the end. Okay, even if it doesn't say that, if it just tells you what two variables change, you can assume that the other two variables do not change. Okay, and this sets us up to something very nice. If my volume over my moles initially is equal to RT over P, and my volume in moles in the second scenario is equal to RT over P, and it's the same RT and P in both scenarios, then what can I say about my volume in moles initially and how that's related to my volume in moles in the final state? So these are, remember those proofs you had to do in geometry and how you were like, when am I ever going to use this? Here you go. You're going to use it right now. We're going to use algebra. We're going to use geometry right now. Okay? If A is equal to B and B is equal to C, what can we say about the relationship between A and C? We can say that they're equal, right? So we can say that, I'm running out of space here, but let me switch colors and maybe you can still follow me. We can say that V1 over N1 is equal to V2 over N2. And now we have just eliminated pressure, temperature, and R. We don't need to know what they are. It doesn't matter, right? Because we have just manipulated our formula and kicked those out of our formula. We just now need to know about volume in moles, and we can plug in 3 of these values and chug out an answer for the 4th one. Like I said, the name of the game is being able to manipulate the formula. So can you run through this same scenario and find what that relationship would be between volume and pressure? Could you do it for volume and temperature? What if volume, pressure, and temperature changed, but moles stayed the same? Could you derive a relationship for volume, pressure, and temperature where moles stays consistent? And here's the power of being able to manipulate the ideal gas law is you don't have to memorize, what would that be, like 12 different formulas, all the different possible combinations of these 4 variables. You don't have to have that memorized. You can memorize one formula, PV equals nRT, and you can manipulate that formula to give you all the other formulas that you need. Okay, so we're going to practice this. Don't worry. That was just your introduction. We're going to practice this, and that's why this chapter is not complicated, but you really need to know the skills, and you're going to learn those skills not by me talking at you more, but by you practicing through these skills and bringing me questions. So we'll practice together in class, but go ahead and do some of your practice problems in the book too, and then you can bring those questions into class, and we can deal with those also. All right. So let's go through this question. For example, this is a very standard question. When I see long questions like this on a test, I always read the last sentence first. How many moles of carbon dioxide gas were generated? So now I know what I'm looking for, and I can kind of go back and backtrack and pick out pieces of information that I'm going to need in order to answer this question. Okay, so go ahead and read it. I'll read it too, and then we'll talk about this. Okay, they give us a reaction, but it's not clear if we actually need a balanced reaction in this. If we're going to do any kind of like dimensional analysis where we switch from one thing to another thing, then we're definitely going to need a balanced equation because we'll need that molar ratio between the two molecules. But if we're never going to convert between two different molecules, if we're always dealing with the same molecule this whole problem, then we don't even need a balanced reaction. So let's not write one yet until we know what we need. So it talks about how the carbon dioxide is collected in a 250 milliliter flask. So our volume is 250. And that is after the decomposition has happened. They also give us a pressure after the decomposition has happened. And they give us a temperature after the decomposition has happened. Oops, that's a 31, not a 3.1. And then they ask us for moles after the decomposition has happened. So all of these things they give us are describing the same point in time, the same context. And they're all describing carbon dioxide. So we don't need to know anything about those other two molecules since we're dealing with carbon dioxide the whole time. So PV equals nRT. If you're not sure where to start, listing them out like I have done is a good thing to do. Another good thing to do that I love doing, which kind of helps me wrap my brain around what kind of a problem it's going to be, is I'll put little check marks. Okay, I have V, I have P, I have N, I have T. All I need is R. That's the ideal gas law constant. I have that. And so I can, I don't have N. Sorry. I'm trying to find N. Okay, I'm trying to find this. I have everything else, and this is a plug and chug problem. Okay, so the first thing I'm going to do is rearrange the equation. Now, I say that, and half of you are going to ignore me unless you've taken physics and it gets pounded into your head. You really should rearrange the formula, solve the formula in variables before you plug and chug. You are less likely to make a mistake. So let's solve it for N, PV over RT. Okay, we have P, we have V. T is in Celsius. We need it in Kelvin. So we're going to add 273, and we're going to get 403 Kelvin. Okay, and now we just plug and chug. So 1.3 atmospheres, 250 milliliters. I need that in liters, so 0.250 liters. R, 0.08206 liter atmospheres, Kelvin, mole. Temperature is going to be 304 Kelvin. And that is going to give me N. And N is going to be right where my face is. So let me go up here. N equals 0.13. How many sig figs can I keep? I can keep 2. And let's see what unit I end in. Liters reduces out, atmospheres reduce out, Kelvin reduces out. I'm left with 1 over moles. So that's going to leave me with moles. Dividing by a fraction is the same as multiplying by the reciprocal, right? Okay, did you beat me there? Very standard plug and chug problem with the ideal gas law. Okay, there's 2 more that we can do together in class, and that brings us to gas density and molar mass. Okay, so gas density, molar mass, this is, again, it's just a manipulation of the ideal gas law. So I want you to start with the ideal gas law. PV equals nRT. And can you manipulate it into this formula where N is over V? Now would be a good time to pause and make sure you can do that. It's good practice. All right, we want N on the top. I'm going to divide both sides by V. So I get P equals nRT over V. I want to get rid of RT. So I'm going to divide both sides by RT. So I'm going to get P over RT equals N over V. Okay, so again, notice that this equation right here is just a manipulation of the ideal gas law. It's not anything new. It's our same one equation used for the purposes that we need it used for. Okay, so now what I want you to take a minute and find out are what are the units that are on this side with moles over volume? It's molarity, right? Moles per liter is molarity. So what we really have is molarity of a gas, concentration of a gas in terms of moles per liter is equal to pressure over RT, gas law constant times temperature. Okay, so now we're going to manipulate it a little bit more. We're going to multiply both sides by molar mass. Now, they use a capital M for molar mass. If you see it in the book, it's going to be a little bit fancier. It'll be like a capital cursive M. Okay, but I couldn't quite find the right font, so I just used capital M. Okay, so if we multiply both sides by molar mass, I'm just going to write it over here. Okay. So that side's going to be P times molar mass over RT. On the other side, I'm going to write molar mass, but instead of writing it as M, I'm going to break it into its units. So what are the units of molar mass? Take a minute and see if you can write that down. Now, molar mass is the mass of 1 mole, right? So it's going to be in grams per mole. So when I multiply this left side by molar mass, I'm multiplying by grams over moles. Now, you should see something in this equation. There are units there that are going to reduce out. Which are the units that are going to reduce out there? And it's moles. So when we do this, when we multiply by this factor, what we're left with is grams over liters. And that is a concept we've talked about before. What concept has the units of grams per liter or grams per milliliter? It's also a measurement of concentration, right? But instead of concentration in terms of moles, it's concentration in terms of grams or mass, which is density. So we have density equals pressure times molar mass equals RT. All right, so it's another formula you have to know. I'm not sure if it's on your reference sheet or not. Definitely worth checking. However, you don't have to memorize it because you can derive it, right? Let's embrace it. I'm telling you, life is easier if you just embrace it. Derive this stuff and you will know it for longer. You will remember it for much longer. And you have to memorize much less, which is always a bonus in my world. This is a formula that they reference a lot on the AP test. They do expect you to know this formula. Like I said, not sure if it's on the reference sheet or not, but definitely worth checking. If it's not, it is definitely something that's worth putting on that last page of your notebook, that sheet of like stuff to review for the test the week before you walk in, or maybe the hour before you walk in. This formula would be a good one to know. It shows up enough on the test to be useful to have it in your back pocket. Okay, so there are lots of questions that we can go pursue in this with this formula. We'll just try one together. We'll try a couple more together in class. And then there's a bunch in your book that you should go through until you feel comfortable manipulating the ideal gas law and kind of deriving this information from it. So what is the density of carbon tetrachloride, CCl4, carbon tetrachloride vapor? So they're telling you it's in a gaseous form, not a solution. So that should be a light bulb that goes off your head. Since it's a vapor or a gas, you can use any derivation of the ideal gas law. 714 torr, 125 degrees Celsius. So it doesn't look like we have a whole lot of information. They want to know what the density is. They give us pressure, 714 torr. They also give us a temperature, 125 degrees Celsius. Okay, so at this point in time, if you were doing these problems, what you should think is, what kind of formulas do I have that involve density and pressure and temperature? Now, obviously, we're going to use the ideal gas law because we just talked about it, right? So you can go through and derive it from the ideal gas law. Now would be a good time. If you remember what we just wrote down, you can also just use that. Okay, so we have pressure, we have temperature. R is a constant, so we have that. We're trying to find density. So the one thing we need is molar mass. Now, do you have it or can you find it? Yes, hopefully you can off the periodic table. So let's go ahead and find that. Plug and chug, get me an answer. Okay, 4.42 is the answer that I got. Now there's a couple things here. Notice that our ideal gas law constant is in liter atmosphere per Kelvin mole. So all of the variables that we're dealing with must be in liters, atmospheres, Kelvin, and moles. So the pressure that we had was not given to us in atmospheres. It was given to us in torrs. You do need to convert it into atmospheres. The temperature that we were given is in Celsius. We need it in Kelvin. You have to convert that also. Now, as I plug it in, I can go back and do a little check to see that I've set it up correctly. If I've set it up correctly, all my units should reduce out except for the one I want, which is grams per liter. So atmospheres will, Kelvin will, moles will, and I am left in grams per liter, which is kind of a self-check. It's definitely a self-check that is worth your 3 seconds to go through and do to make sure that you have gotten the right units and therefore set the problem up correctly. Okay, did you beat me there? I hope you did. We can go through this one together in class. And we are on to partial pressure. Okay, so let's start talking about partial pressure now. Let me just introduce it to you, and then we can kind of continue it in class. So Dalton's law of partial pressure is talking about how do you calculate, how are all the pressures of all the gases in a container, how are they related to a total pressure? And what you can see here is that it's a sum. So gases are super bizarre. They kind of operate on their own principles that belong to them, and they don't share those principles with solids, liquids, and gases. Obviously they're gases, solids and liquids, right? And so this is kind of one of those moments where what we might assume happens doesn't actually happen. So if you have, let's say you have gases in boxes. I don't know. Let's put them in boxes. Okay, so let's say you have 1 liter boxes and you have a whole bunch of gases. You have oxygen in this one. You have nitrogen in this one. You have, I don't know, let's do water in this one. Okay. Now, each of these gases in its own 1 liter box is going to exert a partial pressure, or it's going to exert a pressure. So we'll have the pressure of O2 in this box. Let's say that's, I don't know, 0.4. We'll have a pressure of N2 in this box, and that is going to be 0.2. And then we have, my pen's getting hard to read. I'm going to switch colors here. Pressure of N2 is going to be 0.2. And then we have a pressure of water inside its own box is going to be 0.1. Okay, so each of these gases is exerting a pressure in their own box. When we combine these gases into a new box that is, again, 1 liter. So inside this box, we have the oxygen, we have the nitrogen, and we have the water vapor all mixed together. Those partial pressures are just going to add. That's all. So we're going to take the pressure of O2, we're going to take the pressure of N2, we're going to take the pressure of H2O, and we're going to add them all together. And that, simply enough, gives us the total pressure in that box. So 0.4 atmospheres plus 0.2 atmospheres plus 0.1 atmosphere is going to give us a total pressure, P total, of 0.7 atmospheres. It's really simple. It almost seems too simple, but that's how partial pressures work. Partial pressures of a gas is talking about the pressure that it would exert by itself if it were all alone in a box. And when you put that gas in with other gases, that partial pressure just adds to all the rest of them to give you a total pressure. You can also use this to manipulate the ideal gas law. Bet you didn't see that one coming. Because moles do the same thing. If we have moles of oxygen, nitrogen, and water, let's say we have 1 mole, 2 moles, and 3 moles of oxygen, nitrogen, and water. The total moles in the box, once they're all combined, is just added. So our total moles is going to be 6 once we add them all together. Since moles are additive and pressures are additive, we can take the ideal gas law and that becomes additive too. So notice that we have our total pressure, which is made up of all of our partial pressures summed together. We have our total moles, again, made up of all of our moles added together. And then we have RT over V. So those are our constants when these other two are kind of changing and adding together. So we can look at the ideal gas law in kind of a summative way using these two ideas. Okay, so I'm going to stop there for today. You can go ahead and try a couple of these problems we'll try a couple problems together in class. Please bring your questions. Actually, do we have time? We do not have time. Okay, so we'll start here next time and keep going from here. Good job today, you guys.